Welcome! In this session, we'll explore the problem of optimizing water distribution in a village. This is a fascinating challenge that combines cost efficiency and network optimization. Let's dive in and analyze the best approaches to solve it. In this problem, we are tasked with optimizing how water is distributed in a village with n houses. Each house is labeled from 1 to n, and there are two main ways to supply water to these houses. The first option is to build a well in a house, which incurs a fixed cost specific to that house. The second option is to connect two houses using a pipe, allowing them to share water, which incurs a connection cost based on the length or complexity of the pipe. The aim is to supply water to every house in the village while minimizing the total cost. To achieve this, we are provided with two key inputs: an array wells that specifies the cost of building a well for each house, and a 2D array pipes that lists the cost of connecting two specific houses using a pipe. Our task is to determine the minimum total cost needed to ensure that all houses have access to water. The output for this problem is a single integer that represents the minimum total cost to supply water to all houses. Let's consider an example to understand this better. Suppose the input consists of wells equals 1, 2, 2, and pipes equals 1, 2, 1, 2, 3, 1. Here, we have three houses. The cost of building a well at house 1 is 1, at house 2 is 2, and at house 3 is also 2. Additionally, there are two pipes available, one that connects house 1 to house 2 with a cost of 1, and another that connects house 2 to house 3, also with a cost of 1. The optimal solution is to build a well at house 1 for a cost of 1, use a pipe to connect house 1 to house 2 for a cost of 1, and use another pipe to connect house 2 to house 3 for a cost of 1. This results in a total cost of 3, which is the minimum possible. Let's look at another example to further clarify. Suppose the input consists of wells equals 5, 3, 4, and pipes equals 1, 2, 2, 2, 3, 1, 1, 3, 2. Here, building a well at house 1 costs 5, at house 2 costs 3, and at house 3 costs 4. There are three possible pipe connections: house 1 to house 2 costs 2, house 2 to house 3 costs 1, and house 1 to house 3 costs 2. The optimal solution in this case is to build a well at house 2 for a cost of 3, connect house 2 to house 3 with a pipe for a cost of 1, and connect house 1 to house 2 with a pipe for a cost of 2. The total cost is therefore 3 plus 1 plus 2, which equals 6. This is the minimum cost needed to ensure that all houses are supplied with water. The constraints for the problem ensure that the input sizes are manageable and that every house is guaranteed to be reachable through some combination of pipes or wells. There are additional details to consider when solving the problem. The cost of building a well for any house will always be non-negative and can go up to 100,000. Similarly, the connection cost for pipes is also bounded between 1 and 100,000. The number of houses, n, can be as large as 10,000, and the number of pipes can be up to 20,000. This means the solution must be efficient to handle larger inputs. Each pipe connects exactly two houses, and the input guarantees that every house is reachable. Edge cases to keep in mind include situations where building wells is significantly cheaper than using pipes, in which case the solution will prioritize wells over pipes. On the other hand, if pipe connections are very inexpensive, the algorithm will prefer connecting houses through pipes. Additionally, the solution must avoid redundant pipe connections if cycles exist in the network. Sparse pipe connections combined with high well costs may lead to a strategy that builds more wells rather than relying on pipes. These considerations will ensure that the solution is both correct and optimized for all scenarios. To tackle the problem of optimizing water distribution in a village, we need to focus on the two available options for each house, either installing an individual well or relying on pipes to connect to another house. The objective is to minimize the total cost of providing water to all houses. One straightforward approach to solve this is brute force. Here, we would enumerate all possible combinations of wells and pipes, calculating the total cost for each configuration. Essentially, this involves analyzing each house and determining whether it should depend on a well or pipes, and for pipes, deciding which houses should be connected. While this method guarantees correctness, its major drawback is its exponential time complexity, which is 2 to the power of n. This means that as the number of houses increases, the number of configurations to evaluate grows exponentially, making the approach impractical for larger inputs. Although simple to understand, this solution is inefficient and unsuitable for real-world applications with many houses. A more efficient way to solve this problem is by reducing it to finding a minimum spanning tree, or MST, in a graph. The key insight here is to treat each house as a node in the graph. Additionally, we introduce a virtual node, node 0, which represents the option of installing a well. This virtual node is connected to every house with an edge weight equal to the cost of installing a well in the respective house. The given pipe connections between houses are then treated as edges in the graph, with their respective costs as weights. The problem now becomes finding the MST of this graph, which ensures that the total cost of providing water to all houses is minimized. To implement this, we first construct the graph, including the virtual node and all edges. Then, we use a well-known MST algorithm, like Kruskal's or Prim's, to compute the MST. Finally, the sum of the edge weights in the MST gives us the minimum cost. This approach is computationally efficient, with a time complexity of O(E*log, where E is the number of edges in the graph, and a space complexity of O(E plus V, where V represents the number of nodes, including the houses in the virtual node. By adding the virtual node, we simplify the problem significantly, allowing the installation of wells to be treated as just another type of edge. The MST guarantees a globally optimal solution, as it minimizes the total weight of the tree. The MST approach was chosen because it offers both efficiency and elegance. By leveraging well-established graph theory, we can transform the problem into something that is not only simpler to reason about but also computationally efficient. Other alternatives, such as dynamic programming or combinatorial optimization, could theoretically solve the problem but would require more complex implementations and likely be less efficient. In comparison to brute force, the MST approach is exponentially faster and easily handles larger inputs. However, there are trade-offs to consider. The MST approach is optimal and conceptually clear, but it requires an understanding of graph algorithms like Kruskal's or Prim's, which might be challenging for some. The brute force approach, though easy to understand, is computationally infeasible for larger datasets. Dynamic programming, while feasible, would involve intricate state representations and transitions, making it less practical. Overall, the MST approach stands out because it aligns directly with the problem structure, minimizes complexity, and delivers an optimal solution efficiently, making it the best choice for this problem. To tackle the problem of optimizing water distribution in a village, we first transform it into a graph-based problem. Imagine each house in the village as a node in a graph, and the cost of building pipes between houses as the edges connecting these nodes. Additionally, we introduce a virtual node, labeled as node 0, to represent the option of building a well at each house. This virtual node connects to every other node, with the edge weight equal to the individual cost of building a well at that house. This setup essentially frames the problem as finding a minimum spanning tree, or MST, where we aim to connect all nodes at the minimum possible cost. To solve the MST, we use Kruskal's algorithm. First, we sort all the edges, including those connected to the virtual node, in ascending order by their weights. Then, we use a union-find data structure to manage connected components efficiently. The find operation helps determine the root of a component, and the union operation merges two components. These steps are critical for efficiently building the MST without forming cycles. Once the edges are sorted and the union-find data structure is initialized, we proceed to build the MST. For each edge in the sorted list, we check if the two nodes connected by the edge belong to different components using the find operation. If they do, we add the edge to the MST and merge the two components using the union operation. This process continues until we have added exactly n edges to the MST, where n is the total number of houses. After constructing the MST, we calculate the total cost by summing up the weights of all the edges included in the MST. This total represents the minimum cost required to provide water to all houses. The approach is rooted in two key insights. First, by introducing the virtual node, we convert the problem of selecting between wells and pipes into a graph problem, allowing us to use standard MST techniques. Second, Kruskal's greedy algorithm ensures that we always choose the cheapest available edge, making the solution optimal. The union-find data structure further enhances efficiency by enabling near-constant time operations for cycle detection and component management. To implement this algorithm, we rely on two primary data structures. The graph is represented as an edge list, where each edge is a tuple containing the cost and the two nodes it connects. This representation is ideal for sorting and processing in Kruskal's algorithm. The second data structure is union find, which efficiently manages connected components. It supports two key operations: find, which retrieves the root of a component, and union, which merges two components. Both operations are optimized with techniques like path compression and union by rank, ensuring near constant time performance. Analyzing the algorithm's complexity, the sorting step dominates the runtime, taking E log E, where E is the number of edges. Union find operations are nearly O(1) per operation, and over the course of the algorithm, they contribute E asterisk alpha V, where alpha is the inverse Ackermann function and V is the number of nodes. As a result, the overall time complexity of the algorithm is E log E, primarily driven by the edge sorting step. When applying this algorithm, there are several edge cases to consider. If there is only one house in the village, the solution is straightforward. It simply involves the cost of building a well at that house. For scenarios where the graph might be disconnected, introducing the virtual node ensures that the graph remains connected, as every house has the option of connecting to the virtual node via a well. Additionally, if the cost of pipes between houses is prohibitively high, the algorithm naturally selects the virtual node edges, effectively assigning a well to each house. Let's look at an example to see how this works. Suppose we have well costs of 1, 2, 2 for 3 houses and pipe costs of 1, 2, 1, 2, 3, 1. When we represent this as a graph, we include virtual node edges like 1, 0, 1, 2, 0, 2, and 2, 0, 3, corresponding to the well costs. The pipe edges are 1, 1, 2, and 1, 2, 3. Sorting these edges by cost gives us the list 1, 0, 1, 1, 1, 2, 1, 2, 3, 2, 0, 2, 2, 0, 3. With the edges sorted, we begin constructing the MST. The first edge, 1, 0, 1, connects house 1 to the virtual node at a cost of 1. Next, we add the edge, 1, 1, 2, which connects house 2 to house 1. Finally, we include the edge, 1, 2, 3, connecting house 3 to house 2. At this point, we have added 3 edges, equal to the number of houses, so the MST is complete. The total cost of the edges in the MST is 1 plus 1 plus 1, which sums to 3. This represents the minimum cost required to supply water to all houses. By carefully balancing the costs of wells and pipes using our graph-based approach, the algorithm ensures that the solution is both optimal and efficient. The final output, therefore, is 3, which is the minimum cost to provide water to the entire village. To solve the problem of optimizing water distribution in a village, we can think of it as a graph problem. First, we initialize an empty list called edges to store all the potential connections. To represent the cost of digging a well at each house, we introduce a virtual node, labeled as node 0. For every house, we create an edge between this virtual node and the house, where the weight of the edge is the cost of digging the well. Next, we add the pipes as edges between houses, where each edge is represented by the cost of the pipe and the 2 houses it connects. After building this list of edges, we sort them by cost. This prepares the data for applying Kruskal's algorithm, which will help us find the minimum spanning tree. To manage the connected components during this process, we implement a union find data structure. We initialize a parent array, where each node is its own parent, and a rank array, which helps optimize the union operation. The union find data structure is essential for efficiently managing connected components as we process the graph. The find function determines the root parent of a node, using path compression to flatten the structure for faster queries. The union function merges 2 components if they are not already connected. It compares the ranks of the root nodes to decide which tree should become the parent, ensuring the structure remains balanced. If both trees have the same rank, we arbitrarily choose one and increase its rank. Once the structure is in place, we iterate through the sorted list of edges. For each edge, if the 2 nodes it connects belong to different components, we merge them using the union operation and add the edge's cost to total_cost. This process continues until all nodes are connected, resulting in the minimum spanning tree. Finally, we return the total_cost, which represents the minimum cost to supply water to the entire village. To solve the problem of minimizing the cost to supply water to a village, we can break it down into a graph problem. We start by creating a list of edges to represent the connections. First, we add a virtual node, represented as node 0, which connects to all houses with the cost of digging wells. This is achieved by iterating through the wells array and adding an edge from node 0 to each house with its respective well cost. Next, we include the pipes connecting houses as edges. Each pipe is represented by its cost and the two houses it connects. Once all edges are added, we sort them based on their cost using a comparator, which is a critical step for Kruskal's algorithm. Finally, we initialize the union-find structure to manage connected components, setting up the parent array where each node is its own parent initially, and the rank array to help with efficient union operations. The union-find data structure is key to managing connected components efficiently. The find function helps locate the root of a node with path compression, ensuring that the tree remains shallow and operations are faster. If the current node is not its own parent, we recursively find its root and update its parent directly to the root. The union function merges two components by connecting their roots. If the roots are different, we compare their ranks to decide which root becomes the parent. If the ranks are equal, we arbitrarily choose one root and increment its rank. This ensures that the tree height remains balanced. The union function returns true if two components are successfully merged, otherwise false. With this setup, we can now proceed to find the minimum spanning tree using Kruskal's algorithm. We iterate through the sorted edges, checking whether adding an edge would connect two different components. For each edge, we use the union function to determine if the nodes it connects belong to different components. If they do, we merge the components and add the cost of the edge to our total cost. This ensures that we only include the edges necessary to connect all nodes while minimizing the total cost. By the end of the loop, we will have built the minimum spanning tree, which represents the optimal way to connect all houses with either pipes or wells. Finally, we return the total cost, which is the minimum cost required to supply water to the entire village. This approach efficiently combines graph theory and greedy algorithms to solve the problem in an optimal manner. To solve the problem of optimizing water distribution in a village, we start by representing the input as a graph. Here, we have 3 houses, and the cost of digging a well at each house is given as 1, 2, 2. Additionally, there are pipes connecting the houses with associated costs. To efficiently determine the minimum cost, we introduce a virtual node, labeled as node 0, which represents the option to dig a well at each house. Each house is then connected to this virtual node with an edge corresponding to the well digging cost. For example, house 1 has an edge, 1, 0, 1, indicating a cost of 1 to connect to the virtual well. Similarly, edges 2, 0, 2, and 2, 0, 3 are added for houses 2 and 3. Next, we include the given pipe connections, resulting in edges like 1, 1, 2, for the connection between houses 1 and 2. After combining all edges, we have the complete graph representation with edges 1, 0, 1, 2, 0, 2, 2, 0, 3, 1, 1, 2, 2, 2, 3, 2, 1, 3. To prepare for Kruskal's algorithm, we sort these edges by cost, yielding 1, 0, 1, 1, 1, 2, 2, 0, 2, 2, 0, 3, 2, 1, 3, 2, 2, 3. Finally, we initialize the union-find data structure with each node as its own parent and rank set to 0. Now, we apply Kruskal's algorithm to find the minimum spanning tree for the graph. Starting with the smallest edge, 1, 0, 1, we use the union-find approach to connect house 1 to the virtual well. This updates the total cost to 1, and the union-find structure now has parent equals 0, 0, 2, 3, and rank equals 1, 0, 0, 0. Next, we process the edge, 1, 1, 2, connecting house 2 to house 1. The total cost increases to 2, and the updated structure becomes parent equals 0, 0, 0, 3. When processing the edge, 2, 0, 2, we find that house 2 is already connected through a lower cost path, so we skip this edge. Then, we handle 2, 0, 3, connecting house 3 to the virtual well. This brings the total cost to 4, and the final union-find structure is parent equals 0, 0, 0, 0. The remaining edges are skipped as all nodes are now connected. Hence, the minimum cost to supply water to this village is 4. In the case of a larger village with 4 houses, we follow the same approach. Here, the well digging costs are 1, 2, 3, 4, and the pipes with their respective costs are also provided. As before, we begin by representing the graph. Virtual edges connect each house to the virtual well, resulting in edges like 1, 0, 1 for house 1 and 2, 0, 2 for house 2, and so on. The given pipes are represented as edges such as 1, 1, 2 for the connection between houses 1 and 2. Combining these, the graph includes edges 1, 0, 1, 2, 0, 2, 3, 0, 3, 4, 0, 4, 1, 1, 2, 3, 2, 3, 4, 3, 4, 2, 1, 4. Sorting these edges by cost produces the sequence 1, 0, 1, 1, 1, 2, 2, 0, 2, 2, 1, 4, 3, 0, 3, 3, 2, 3, 4, 0, 4, 4, 3, 4. With the graph prepared and edges sorted, we're ready to apply Kruskal's algorithm. Using Kruskal's algorithm, we process the sorted edges to construct the minimum spanning tree. Starting with 1, 0, 1, we connect house 1 to the virtual well, adding a cost of 1. Next, 1, 1, 2 connects house 2 to house 1, increasing the total cost to 2. The edge 2, 0, 2 is skipped since house 2 was already connected through a lower cost path. Then, 2, 1, 4 connects house 4 to house 1, bringing the cost to 4. Finally, 3, 0, 3 connects house 3 to the virtual well, increasing the total cost to 7. The remaining edges are skipped as all houses are now connected. Thus, the minimum cost to supply water to this larger village is 7. To analyze the time complexity of our solution, we break it into 3 main steps. First, during graph construction, we add edges for wells and pipes. Since iterating through the wells array takes O, n, and through the pipes array takes O, m, the total time for this step is O, n plus m. Next, we sort the edges. The edges list contains n plus m edges, and sorting this list takes O, n plus m, asterisk log, n plus m. Finally, we perform union find operations as part of Kruskal's algorithm. For each edge, the find operation runs in O, alpha, v, where alpha is the inverse Ackermann function, which is nearly constant. Since we process all n plus m edges, the total time for this step simplifies to O, n plus m. Combining these steps, the sorting phase dominates, leading to an overall time complexity of O, n plus m, asterisk log, n plus m. Now looking at the space complexity, we start with storage for edges. The edges list contains n plus m edges, each taking constant space, so this step requires O, n plus m, space. Then, the union find data structure uses 2 arrays, parent and rank, each having a size of n plus 1, resulting in O, n, space. Additionally, there are a few temporary variables like total underscore cost and loop iterators, but these take only O1 space. Adding these contributions together, the total space complexity sums up to O, n plus m. The total space complexity of our solution is therefore O, n plus m. To better understand the efficiency of this approach, let's compare it with a naive method. A brute force approach might consider all possible combinations of wells and pipes to find the minimum spanning tree. This would involve evaluating all subsets of edges, leading to an exponential time complexity of O, 2 caret, n plus m, which is computationally infeasible. In contrast, the optimized approach with Kruskal's algorithm reduces the problem to sorting edges and using the union find structure to manage connected components. This makes the solution highly efficient, with a time complexity of O, n plus m, asterisk log, n plus m, and a space complexity of O, n plus m. Finally, let's consider the best, average, and worst cases for this algorithm. In the best case, the number of edges is minimal, for example, if we only have wells and no pipes. Here, sorting the edges is faster, and the time complexity reduces to O, n asterisk log n. In the worst case, we have a dense graph with many pipes, maximizing the number of edges at n plus m. Even in this scenario, the time complexity remains O, n plus m, asterisk log, n plus m, since sorting dominates. The algorithm remains efficient across all cases because union find ensures nearly constant time operations for managing connected components. Mathematically, the sorting step, which takes O, e asterisk log e, where e equals n plus m, governs the final time complexity. Union find operations, nearly constant per edge, contribute O, E asterisk alpha, V, where V equals n plus 1. Therefore, the overall time complexity is determined by the sorting phase, O, n plus m, asterisk log, n plus m. When working on this problem, there are a few common mistakes to watch out for that can significantly impact the quality of your solution. One major error is overlooking the house with well cost as a node in the graph. The cost of installing a well at each house should be treated as an edge connecting that house to a virtual node. Ignoring this means you're not fully representing all possible connections in your graph, which will lead to suboptimal solutions. Another common mistake involves using the wrong algorithm for finding the minimum spanning tree. Algorithms like DFS or BFS are great for traversal but aren't designed to minimize edge weights globally. Instead, you need to use Kruskal's or Prim's algorithms, as they are specifically built for this type of optimization. Finally, when using Kruskal's algorithm, failing to sort the edges by weight before processing them is a critical error. The algorithm depends on processing edges in ascending order of cost to guarantee an optimal solution, so skipping this step will result in incorrect outcomes. Another frequent mistake is ignoring edge cases. For example, consider scenarios where all houses rely solely on wells or only on pipes. These edge cases test the extremes of your algorithm and ensure it handles unique situations correctly. Failing to account for them can result in bugs or inefficiencies. Additionally, inefficient union find operations can slow your solution down considerably. If you're not applying optimizations like path compression or union by rank, the operations in the union find data structure can degrade to O, N, which drastically impacts the performance of Kruskal's algorithm. These optimizations are crucial to maintaining efficient runtime and ensuring that the algorithm scales well with larger inputs. For interviews, there are a few key points to keep in mind with this problem. First, it's essential to recognize that this is a graph-based optimization problem, and a strong understanding of minimum spanning tree algorithms like Kruskal's or Prim's is necessary to solve it effectively. Another important insight is recognizing common patterns in graph problems, such as adding a virtual node or edge to simplify constraints. This approach is not unique to this problem and can be applied to many other graph-based challenges. A common follow-up question you might encounter is, what if the cost of installing a well changes dynamically? How would you modify your approach? This question tests your adaptability and depth of understanding, so be prepared to explain how your solution could account for such changes. Lastly, be ready to discuss the efficiency of your implementation. For example, Kruskal's algorithm combined with an optimized union find has a time complexity of O, E asterisk log, where E is the number of edges. Highlighting this level of detail demonstrates a thorough grasp of the problem's computational demands. This problem is closely related to several other graph optimization problems, which can give you additional practice and insight. For example, LeetCode 1584, min cost to connect all points, and LeetCode 1135, connecting cities with minimum cost, also involve finding minimum spanning trees. LeetCode 684, redundant connection, focuses on cycle detection, which is a key component of Kruskal's algorithm. Exploring these related problems can deepen your understanding of graph concepts and techniques. In terms of alternative approaches, Prim's algorithm is another option worth considering. It works well for dense graphs and grows the minimum spanning tree incrementally from a starting node. However, it relies on an efficient priority queue, and its complexity is O, E plus V asterisk log V. On the other hand, Kruskal's algorithm is better suited for sparse graphs because it processes edges in sorted order. With a complexity of O, E asterisk log, it's highly efficient when combined with a well-optimized union find structure. Both approaches have their trade-offs, so choosing the right one depends on the graph's characteristics. Finally, there's the greedy direct optimization approach, which involves comparing the cost of installing wells versus pipes for each house individually. While this method might seem intuitive, it doesn't scale well for larger inputs or more complex graphs. This is because it doesn't guarantee a globally optimal solution, as it focuses on local decisions without considering the broader structure of the graph. For smaller problems, it might work as a quick heuristic, but for competitive programming or interviews, relying on Kruskal's or Prim's algorithms is the better choice for ensuring accuracy and efficiency. Understanding these trade-offs is key to selecting the most suitable approach based on the problem constraints and requirements. In conclusion, we tackled the problem of optimizing water distribution in a village using a minimum spanning tree approach. By understanding the trade-offs and focusing on cost efficiency, we've built a strong foundation for solving similar network optimization problems. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!